configuration detail. But you guys are going to need this for the project. Okay, detail. Right, so this is our simple implementation. All right, and it's actually called edge label compression, right? So another name for this is edge label compression. The way that it's written in Gusfield is a bit different from what I'm giving you guys, but I prefer that you use the version that it's on the project, okay? Because what Gusfield does, he only stores the edge labels. And instead, I store the path labels, meaning that I store a pointer to the first letter that's close to the root, okay? And it turns out that when you do your suffix tree implementation, it's going to be easier to store the path labels instead of the edge labels, okay? All right, so questions there? No? Okay, so if there are no questions there, then we can move to a Conan's algorithm. Okay, it turns out that the Conan's algorithm is essentially the algorithm that we saw in the previous class. It actually is in the project, so I'm going to use the project. We only have the path label. How do we know where the edge starts? Right. So yeah, very good question. Good question. If we only have path labels, okay, how to know where an edge starts? Level starts. Right. Okay, so this is a good question. Okay, so if we only have a path level, how do we know? How do we know this solution uses linear space? Okay, so how do we know that? Okay, so that's a good question. Okay, so this question, right? So if you only have the path label, how do we know where an edge label starts? Right, suppose that you have something like this. So this is your suffix tree, right? And you have like A, B, C, D, and I don't know, E, F, something like that. And your string looks like this, like A, B, C, D, E, F, right? And now suppose, okay, so I'm going to number this with indexes, right? So, all right, this cannot be. So I'm on a new node, so no reason for you to do this. Okay, so the answer to this question is, so suppose that I want to read EF over here. Can you guys see the EF?
Yes.
Okay. Right. So suppose that I want to read EF over here. What I know is I know the string depth of this node and of this node. I know the S depths, right? Okay, so I know the S depth of this node and of this node. Okay, and 5 and 6. So if I know all of these S depths, I can basically use this S depth. Okay, so this S depth is 2, and this S depth is 4. Okay, so this one actually I don't need, but that's fine. Okay, for this node, the head value, what's the head value here? Okay, so this head value would be AB. Okay, so this one actually we don't know. Okay, we can know. AB, EF, okay, and I don't know, CD, something else over here. Okay, so but the head value here would be 1, right? And the head value here would also be 1, right? Okay, but now suppose that I want to read EF. What do? I'll go to my string S, okay, I go to my head because I know that the head tells me the first letter, so basically gives me this A up here, right? So it gives me this A. But then I add this string depth. Okay, so I add 2, right? So I add this string depth over here. And then I actually have to subtract 1. But the 1 is always fixed, right? So if you need to read an edge label, basically use this expression, right? So S of head, okay, plus S depth of the parent, okay, and then subtract 1. So this is the expression that you use to read the edge labels, okay? I hope this was a convincing response. Was this okay?
Yes, it was
Right?
clear. Thank you.
Okay. Okay. Right. So there was another interesting question here in the chat, which was, let me see, which was, how do we know this solution uses linear space in the general case? Okay, so how do we know that this is linear space? Okay, so for that we can actually use the project, right? So look at here at the project. So this is a struct node, right? So this is all the information that we store in a node. Okay, so it's one integer, another integer, another integer. This is a pointer, which is basically another integer. This is also a pointer and a pointer and another pointer, right? So in total, we have 7 fields, right? And each of the fields is just either a number or a pointer, okay? So a number or a pointer requires either 32 or 64 bits, right? Like 64 bits, fine. But the point is that it's constant, right? So in this case, okay, in this case, we store uh, a constant number of information, O1 information, okay, at each node. Okay. Now, how many nodes are there in the suffix tree? Okay, so how many nodes?
We're still seeing the PDF.
Oh, sorry. So how many? Okay, so in this case, we store O1 information at each node. So how many nodes are there in a suffix tree? Okay. So how many nodes are there in a suffix tree? Right. So this. Okay, because basically we want to say that the total amount of space that we need equals the number of nodes. And we want to say that the number of nodes are linear, right? So how many nodes are there in a suffix tree?
There are n leaves because each leaf is a
right,
suffix.
right? And how many internal nodes?
At most, the number of leaves.
Exactly, right? So in total, at most 2n nodes, okay? Where n is the size of S, right? Okay, so where basically we have n leaves and n less than n internal nodes. We have exactly n leaves and less than n internal nodes. So in total 2n, right? Okay, so this means so with edge label compression, the suffix tree requires at most on space, right? So okay, so the amount of space is the size of the string that you're trying to represent. Okay, so now we can move to a Conan's algorithm. Okay, and basically I gave you guys a Conan's algorithm in the project, so you can look at here, and here's the Conan's algorithm, right? So a Conan's algorithm is essentially the algorithm that I gave you guys in the previous class, right? So basically, what is it? So we have this J here, which is an index, which is basically going through the size of the string, right? So this is going to go through all the letters in the string that we are trying to insert, okay? And then it basically is the same code that we had before, except that we have this new line over here, which is called add leaf, okay? I'm just going to copy that code here to the tablet, and basically we're going to talk about it. But the only thing that we have extra is this this new operation, which is add leaf. Okay, so the idea of add leaf is that so the way that the Conan's algorithm is working, it's inserting one letter at a time, right? So it's inserting the rightmost letter at a time. Like we saw that it's going to change an implicit suffix tree into an explicit suffix tree, right? And so it basically is inserting one letter at a time. Okay, from left to right. Okay, so it's inserting the letters from left to right. So when it's inserting letters, it might need to change the tree structure. Okay, so that's what the add leaf is doing. So basically, let's just do that, right? So J equals, okay. Okay, so we basically have, okay, so I'll just do a 4. Okay, 4, I'm just going to put J. I'm going to change the code a little bit, just so it's a bit simpler, because here in the project, what we're doing is building something called the generalized suffix tree. And we're also going to talk about it, but it's a bit more complicated than a general suffix tree. It's not that much complicated. It just means that you have to use different terminators. Okay, so that's basically the definition of generalized suffix tree. Okay, but we have this code here. Okay, so while we're not able to descend from P, okay, with the given letter that we're using right now.
We are not using the tablet, I think.
I know. I'm just copying and then I'll show you guys. Okay. So while we're not being able to descend, thanks. And then basically we have this new line, which is the add leaf. Okay, and so from the point, and here we're just using the, okay, so here actually you have to give stuff, right? So, but I'll talk about that. And then suffix jump. Okay, here it actually says suffix link, but we said suffix jump. So maybe I have to change this in the project. I'll publish a new version. Okay, so this suffix link is not actually just a suffix link, it's the suffix jump, okay? Okay, I'll do that and publish a new version. Okay, and then basically just descend. Okay. And then just do J++ and finish, right? So, okay, let me show here. Okay, so this is basically what we had in the project, right? So notice here that actually what the project says is suffix link is, it's actually what we've been calling the suffix jump, right? So it's not just a suffix link because you're in a general point and you don't know, and it might not be a suffix, it might not be a node, right? So you have to use the skip count trick. Okay, so that's the idea. Okay, this doesn't do anything. Okay, so here is with the skip count. Okay. Okay, so this is the new operation that we have now, which is the add leaf. Okay, so basically let's emulate this algorithm and see what the add leaf would basically do. Okay.
Just one question.
Yeah.
In this algorithm, since you are using a 4, there's no need for the final J++, or is it duplicate?
Right. I copied and there was ++ there, thanks. Okay, so no need for this one. I copied from, I changed that, and then I copied from the project, and I forgot. Okay, right, so this one, okay, thanks. Right, so this is basically so the first cycle is a for, but this cycle over here is the one where you add the leaves. Okay, so let's suppose that I do this for the string with just a bunch of A's, right? Okay, so and then we're going to put the dollar, right? So what does our Conan algorithm do? Right, so what it does is it starts at the roots, okay, and then okay, so basically we have the roots, which is this node over here, and then we have the suffix link of the root, which is the other node over there that you can get back here, but that's fine. Okay, so we start with our point here, okay, and we try to descend by the letter A, okay. Because I'm not able to descend, I would just follow the suffix link. But because now we have this add leaf instruction, that basically means that I'm essentially going to add this branch, okay? And it's going to contain all the letters here until the dollar, right? So it's sort of contains all the letters. More or less, basically, there's in the book, you're going to see a discussion between a Conan's algorithm and McCrite's algorithm. And they're basically independent rediscoveries of the same algorithm. And it turns out that the difference between the two is that a Conan assumes that you only insert the A, okay? And McCrite assumes that you insert all of the letters, right? And it doesn't make a difference because the way that you insert them is with the edge label compression. So you basically just put a number there. So if that number represents just one letter or all the letters, it's not a big difference, right? So, but that's the difference between a Conan's. Well, there's more differences because this sentinel over here came from a Conan's algorithm. It was not on McCrite's, but you can basically use it here also. But this is the main difference. Right. So the difference between a Conan and McCrite, this McCrite puts all the letters, and a Conan is sort of incremental. Okay, so incremental just means that it only puts one letter, but it assumes that when you put the next, when you insert the next letter, all the suffixes grow a little bit. Okay, but we're basically going to assume like, well, it makes more sense to use the incremental because it matches the definition of implicit suffix tree. So let's just use the incremental as a Conan does, okay? Because if it's incremental, it's an implicit suffix tree. If you assume that you insert everything, then it's not actually a suffix tree. It's just some weird structure. Okay, so let's use a Conan, right? Okay, so insert the A. So basically what our code here tells me is that I should go to do a suffix link, suffix jump, which basically means that I go there. And then I'm finally able to read this A by going back to the root. Okay. Now I'm going to try to read this A. When I read this A in this edge label, I'm able to do that. And therefore my point moves here. Okay. And moreover, because we're being incremental, okay, that also means that a new way pops up here. Okay. And so now I'm going to try to read. No, wait. Well, okay. So this letter I had to go up and down. Okay. So I was able to read this letter, right? So now I'm going to try to read this letter, and I'm able to do that. So I basically just go there, and a new way pops up here. Okay. And then I'm going to try to read this letter, and basically means that my point goes here, and then a new way pops up over here. Okay, and now I get to the point where I want to read the dollar. So I'm here, So my point is now here, and I want to read the dollar. So here I'm not able to read the dollar, right? Because if I try to go down, there's only an A, okay? And therefore, because I'm not able to read the dollar, so what our algorithm tells us to do is to add a leaf. So basically it adds a node here, which corresponds to the leaf that ends in dollar, right? And also a dollar pops up here, okay? But then I do the suffix jump thing, right? So I create this node and then I do suffix jump. Okay, so basically what suffix jump means is that I have to use the skip count trick, okay? So if I use the skip count trick, it takes me here to this position, right? So now my point is here at this position. And again, I'm going to try to read the dollar, right? So again, I try to read the dollar. And again, I'm not able to read the dollar at this point, right? Okay, so there's no node there. It's just a point. It takes me there. So again, I'm not able to read the dollar at this point, and therefore I create a new node with the dollar, and I insert it here. And again, I do the skip count trick, and my point moves here. Okay, and then I repeat. So I try again to read the dollar. I'm not able to read the dollar. That means that I create a new leaf, okay, with the dollar, and my point moves here. Okay, and then I try to read the dollar again. I'm not able to read the dollar, so I create this new leaf. Okay, so this add leaf actually might create two new nodes, right? So notice here when I created this node, when I inserted this leaf, I also had to create that node, right? So add leaf might create two nodes. Okay, so may create two nodes, right? So it may create one leaf. Okay, it not may create one leaf. It always creates one leaf, and it might create an internal node. In this example over here, it didn't create an internal node. It just created the leaf, right? So the last one only created the leaf because the internal node already existed. But the other ones created the leaf and the internal node. Okay, is this more or less clear? Yes. Okay, so the codes that we need to create a suffix tree is essentially the same code that we used, for example, to solve the longest common substring problem. Okay, the only thing that it's new here is this operation. Okay, so if we want to do a time analysis of the algorithm to see how long this algorithm takes to run, all that we care about is that this new operation is constant, because all I'm doing is inserting two new nodes into the suffix tree, right? And inserting two nodes is a constant time operation. And therefore, we should be golden to say that the Conan's algorithm runs in time. Okay, so this algorithm requires or takes O of n time to execute. Okay. So this is basically because of last classes. Okay, last class. This has like a analysis, and the fact that add leaf Okay, requires of one time. Okay, right? So add leaf is constant, right? But there is another nuance. Okay, so the analysis here is the same analysis that we did last class. Just define the potential function that is twice the string depth minus the tree depth, and you can amortize all of this stuff. But there's a nuance, okay? And the nuance is here in the suffix jump operation, which is the following. Notice here, when I'm building this tree, at some point I create this node here in red. Okay, so at some point I create this node, and then I need to compute suffix jump from this node. The problem is that because I have just created this node, it still doesn't have a suffix link. Okay, because I created this node, and this node over here still doesn't exist. Right, so if we draw the suffix links here, the suffix link should be like this. Right? Okay. So the suffix links should go like this, right? But when I create this node here in red, this node, which is the destination of this suffix link, still doesn't exist. Okay. So there's a nuance both in the implementation and in the analysis, where the time that we take to do this suffix jump, okay, actually needs to be fixed because the destination of the suffix link still doesn't exist when I create the node, right? But that's all possible to fix, okay? And I'm just going to write this here. There is an important detail that when a node gets created, its suffix link target might not yet exist. Okay, right? So in general, we know that every node has a suffix link. We proved this in the previous class, but during the construction, those nodes might not exist when we are creating a node. Okay, that means that there's some catching up that the algorithm has to do, right? So when it creates a new node, it needs to go back to see if this new node is actually the suffix link of some other previous node, and then basically fix the link, right? That's it. Okay, questions here? No, sort of makes sense.
And how do we actually do that? The going back and fixing?
Right. So basically, it basically means that you just need to store one memory position, which is last created node. And whenever you create a new node, you go to the last created node and check if it has a suffix link or not. If it has a suffix link, then just don't do anything. If it doesn't have a suffix link, you basically put the new node as the suffix link of the previous one, right? So it's something that you do here in the add leaf. So each time you do an add leaf, each time you create, you might create a new internal node or not, but every time that you call the add leaf, okay, it needs to go to the last created node and check if it has a suffix link. If it doesn't have a suffix link, it basically needs to put the current node as the suffix link of the one that still doesn't have a suffix link, okay? So I can put it here. This needs to be fixed or handled in the add leaf function. Okay, so basically it means that you need to keep you basically need to keep one variable, which is the last created node. Okay, and whenever the add leaf, okay, if the add leaf creates a new node, then the last created node changes to the internal node that the add leaf created. If the add leaf doesn't create a new internal node, then the last created node doesn't exist. Like it goes to null, right? Because you called add leaf, you didn't create anything, then there is no last created node. Okay. All right. So we're basically almost there. So the last thing that I want to talk about is generalized suffix trees. Okay. So section 6.4. Okay. Generalized suffix trees. Okay. Okay. So what's a generalized suffix tree? So a generalized suffix tree is the suffix tree of several strings at the same time. Okay. So basically the idea is build a suffix tree for several strings simultaneously. Okay, so let's take an example over here. Okay, so assume that I have two strings, right? So string 1, okay, x a b x a, right? And you have string 2, right? b a b x b a, right? So suppose that we have these two strings. Okay, so the way that we actually do this in practice is just use different terminators. Okay, so in practice, use different terminators. Okay, actually in practice, the project has actually a neat trick, right? Which doesn't really use different terminators, but okay, so this is okay, so I'll take this in practice out. So the idea is just to use different terminators. In practice, we do something even a bit more tricky, right? So basically we're assuming that terminator 1 and terminator 2 are actually different, right? So the two terminators are different. And so what would we do? We would basically build a suffix tree for both strings, and it should be all in the same tree. This will be necessary to implement the common longest substring between two strings. For the longest common substring between two strings, you can just use what we talked about in the previous class. But actually, what I ask you guys to do in the project is the longest common substring between more than two strings, like longest common substring between 3 and 4 and 5 strings. And therefore, we are going to need this generalized suffix tree. But it's also possible to use this to solve for two strings, right? It's just that it's a bit more powerful and it allows you to do for more than two strings. But it also allows you to do for two strings, right? So let's look at an example here. So basically, what you would do to build this suffix tree, you would basically build one suffix tree. So you build the suffix tree for the first string, and then you would go and you start building the suffix tree for the second string on the same tree. Okay. So what would it look like? It would look like something like this. And actually here in the book, it's incomplete. right? So in the book here is incomplete. Right, so right, so one of the strings is XA. Okay, so I'll copy this. So XA BXA. Okay, so this is $1. Okay, and then XA is also $1. And then XABA. Okay, so XABA is on the second string, right? So no. Where is XABA? No, it's not XABA, sorry, it's XBA. Okay, so XBA is on the second string, right? So it's here, right? So XBA is this suffix here on the second string, right? Okay, so what else do we have? We have A, and then we have, okay, so where A is a suffix of both, right? So it's going to appear with $1 and with $2, right? So it's going to appear with both the terminators, right? Actually, in the book here, where they use the same terminator, but they just give a generalized, they just say that it should have all the suffixes. But I prefer that you guys use the different terminators, okay? Okay, then we have BX, right? And then we have BA dollar. Okay, so what dollar is this? This is ABX BA. ABX BA. Okay, ABX. Okay, so this is $2. Okay, ABX BA. Okay, so if it's ABXA, then it's $1. All right, and then we have the rest here. So we have B, the node, then X, then a node, and then we have $1. Okay, and which dollar is this? So what is BXA? BXA is on $1. Okay, so this is $1. Okay, then BXABA. Okay, so BXABA is on $2. Okay, and this tree is almost complete, where you have the A, and here you have just $1. Okay, so what ends in BA? $2 ends in BA. Okay, and then you have BX, BA dollar, and this one is BA, BAX, BA, what? BA, BX, BA, BA, BX, BA. This is $2, right? So this would be the generalized suffix tree for these two strings, okay? So basically, it's the tree that, so in general, it could be for more than two strings. Here we have two strings, but it can be K, right? So here we have two strings, but it could be any number of strings that you want to add in the same suffix tree. Now, this generalized suffix tree, okay, so here it's the root, okay, and here you have both $1 and $2. $1 and $2. Okay, this generalized suffix tree is useful to can also be used to identify the longest common substring of two strings. Okay, so can also be used to find the longest common substring between of, okay, so f of S1 and S2, right? So how would I use this tree, okay, to find the longest common substring of the two strings, right? Okay, so actually this should be easy to illustrate, right? So suppose that I have these two strings and I want to find the longest common substring, right? So what would I do? Okay, so basically I'm just going to assign different colors to the different strings, right? So I'm going to change this terminator here to an orange, okay? And that terminator to I'll keep it in purple, right? So now what I'm going to do is I'm going to paint all the suffixes with their colors, right? So this $1 would be painted orange, and this would be painted orange, and this would be painted orange, this would be painted orange, and orange, and orange, right? So now what I'm going to do is for each internal node, okay, I can go bottom up, right? So for each internal node, if all its children have the same color, then I'm going to move the color up, right? So this one has only orange, right? And that's basically it. Okay, so now I'm going to paint the purple ones, right? So now I'm going to paint these guys. Right, so this is purple, and this is purple, this is purple, right? But now this one is purple, and this one is purple, and this one is purple, okay, and this one is also purple, and that one is purple, right? Okay, so now what do we have? Okay, so the leaves are painted according to the suffix that they belong, right? But for example, this node over here is not painted. Why is it not painted, right? So why is this node ABX not painted?
Because it appears both in S1 and S2.
Right, okay. So I didn't paint them because its children have two different colors, right? So this one I did paint, right? So this one I painted because both of them had the same color, right? But this one I didn't paint, right? So what this means is that on this configuration, it means that the path label of this node occurs both in S1 and in S2, right? So the nodes that are not painted, the white nodes, okay, white nodes are substrings, okay, of both S1 and S2, right? So the ones that I didn't paint are substrings of both, right? And that means that the node that is not painted, so the white node that has the largest string depth, okay, so the one that has more letters in it, is the longest common substring, okay? Hence, okay, so identify the node, so you're right, so it needs to be an internal node, okay? So identify the internal node, okay, which has both S1 and S2 descendant, okay, which has both leaves, okay, which has both leaves from S1 and S2. Okay, identify the internal node that has both leaves from S1 and S2 and the largest string depth value. Okay, right. So, and this is actually, let me see where this is in Gusfield, right? So this is longest common substring of two strings. This is actually the algorithm that is shown in section 7.4, right? So this is section 7.4. Okay, the algorithm that we saw in the previous class was the one that is in section 7.9. Okay, but this one is the one that is in 7.4. Okay, right. So in this case, this one is the node that is deepest and that has both suffixes from S1 and S2, right? And therefore, this is the longest common substring. So I'm saying that ABX is the longest common substring. Okay, so it occurs here, right? And it also occurs here, right? And that's the longest common substring. Okay. Okay, so questions? Okay. Is this sort of okay?
Makes sense, yes.
All right, so now I can give you guys the algorithm that I actually ask you to do in the project, right? Which is not this one, but the longest common substring of k strings, right? So not of two strings, but of k of them, right? So I'll give you an example. Okay, so section 7.6, right? So this is section 7.6, okay? Common substrings of more than two strings. Of more than two strings. Two strings. Okay, so here's an example. Okay, so 127. All right, so the common substrings of more than two strings. So here's an example, right? So suppose that I have this set of strings, right? So okay, so suppose that I have these strings. Okay, so I have S1, which is $100. Okay, I have S2, which is send what? Okay, I have S3, which is handler. Okay, and I have S4, which is brand. And I have S5, which is pantry. Okay, and now I want to build a little table, right? So I want to build a table that tells me, okay, so I'm basically going to say K, which is the number of strings that the substring should appear on. And I'm going to use LK to mean the size of the string, okay? We can also use an example, but we don't always need to, okay? So Suppose that I want the longest substring that appears in at least 2 of these strings, right? Okay, so what do you guys think that is? Okay, or you can check Gusfield, it will tell you what it is. Okay, so I need a string that's a substring of 2 of these guys, and that's longest over all such possible substrings, right? So what is it?
Sand.
Sand, right? So sand over here appears in 2 of them, and it's actually the biggest one that you can get, right? Now, what if I want to force my substring to appear at least in 3 of them? Right.
Professor, could you explain again what the LK means?
Okay, so this is the size. Oops. Okay, size of the substring. Size of the substring.
Okay, thanks.
Right, so this is the size. Right, so how big is it? It's 4 letters, right? So sand is 4 letters. Now, if I wanted to appear in 3 of them, then I'm out of luck because sand only appears in 2, right? So I need to find another string, right? Okay, what can it be?
And
And, right? So I have and over here, and over here, and over here. So actually it appears in 3, and it also appears in 4, right? And so and is actually this one, right? And it's also this one. Okay, so if I wanted to appear in 4 of them, then it's also and, right? It appears in 3, it also appears in 4, right? Okay, but what if I wanted to appear in all of them, right? So if I wanted to appear in all of them, then I'm out of luck because and doesn't appear in S5, right? So and so I can't use and, right? But I still want it to be the longest, right? So what would the string be?
N.
An, right? So an is the string that appears in all of them, right? So an appears here, and because it appears in and, it appears on all the others, right? Okay, and this is the largest one that you can get, right? So this is 2, and it's an. Okay, now how would I go about building this table, right? So in essence, we want a linear time algorithm, right? So we want an algorithm, okay, that fills this table. Okay, so how much time do we need to fill this table, right? So first we need to build the suffix tree, right? So we have a string 1, we have a string 2, you have a string so on until you nk, right? Okay, so this is size of S1, this is size of S2, okay, and so on and so forth. So this is size of Sk. Okay, so first we need to build the suffix tree, right? So ideally, this would be the time that we wanted, okay? The problem is that our algorithm is going to be a little bit more complicated, right? And actually there are 2 different here. Okay, so So gas field has a small k and a little k. Okay, so the small k is, sorry, small k and a big K. So the small k is actually the values that you put here, right? And the big K is the number of strings that you've got, right? So I'm going to use the big K over here. Okay, right, so big K, number of strings, in the inputs. Okay, so basically the idea is that you make your little k vary from 2, okay, because for one string it doesn't really make sense, to your big K. So our big K over here would be 5, right? All right, so ideally we want this, but we can't actually get it. Okay, right? So instead we're going to allow. Okay, so what's the problem here? So the problem is that this is the time that we need to build the generalized suffix tree, right? But besides building the generalized suffix tree, we need to do some processing, right? So like we did over here, where we painted the nodes, okay? Instead, we're going to do some processing at each node. And that processing means that we have to store more information, right? So it means that for each node, we're going to have to store a table of size k, right? And that means that this is the time that we're going to allow, okay? So at each node, I need to store a table with k elements. Okay, so what's this table? What is stored on this table? Okay, what do you think are the k elements that I'm storing on each node?
Professor, sorry. You inserted a multiplicative constant inside of the O. Isn't that indifferent?
No, because it's a variable of your input, right? So, and one is a variable of your input, right? So if you give it larger text, your algorithm takes longer, right? But k is also a variable of your input, which is how many different texts are you going to give it, right? If you're only going to give it 2, then it would be a constant and it would go away. But the issue is that this works for any k, like 2, 3, 4, 5, so on. And therefore I need to say, I need to have it there as a parameter, right?
Okay.
Was this a good explanation? In case
yes,
of
thank you.
a tie, in other words, if there are more than one common substring within k string, we report all or just the first. Okay, so that's a good question, right? So I have a question here saying that what am I going to ask you guys in the project? Okay, so in the project it is shown what I asked you, and it's not the strings, right? So I don't ask you for the strings, right? So I'm not sure what you're seeing. Are you seeing the project or my tablets?
The project.
Okay, right. So here, what I ask you for the output, if you look here at the output, is just numbers, right? What that corresponds is that on this table, I only want to know these LK numbers, right? I don't want to know what are the strings. I just want to know how big they are, okay? Right, so that was a question. I'm not sure if the question was how do we do it, or if it's only for the, or how do we do it for the project?
Both.
Okay, right. So for the project, you don't have to worry, right? So for the project, you only need to return the numbers, right? So if there are several strings that have the property, then basically I don't care, right? So I just want to get the numbers. In general, for the algorithm, when I said here, identify the the internal node, okay, this was actually not correct, okay? So what I should have said is identify one internal node, right? So identifying one internal node which has both leads and that it's and the largest string depth. But if you identify all such nodes, then you will identify all such substrings, okay?
Okay. Thank you,
Right?
Professor.
You're welcome. Okay. Right, but we still have to see what information do I need to store at each node, right? So what should I store in my, what should I store at each node? So here I only had two different strings, right? So I have these white nodes, which are the nodes that have descendants of both strings, right? But if I have k different strings, I want to store all the possible configurations, right? So basically what I want to do is for each node to store one bit for each possible string, okay? And to say, does this node has descendants of one string, of this string, yes or no, right? So let's do an example here, right? So I'm pretty sure this was not clear, right? So does the root have descendants of type? Okay, so I'll use orange and purple. So this makes sense. Does the root has descendants of type 2? Right?
Yes.
Of string 2. Yes. Sorry, this should be string 1. Sorry. It also has descendants of string 1, right? And does this one has descendants of string 1? Yes. Right? And this one also, and this one also. Right? So all of these have descendants of string 1. Does this one have descendants of string 1? No. Right? This one does, this one doesn't, this one does, and this one does. And what else? This one doesn't, and this one does. This one doesn't, and this one does. This one does, has descendants of type 1. This one also does, this one also does, this doesn't, and doesn't, right? And now for type 2, right? So for descendants of type 2, right? So here, so this one doesn't have descendants of type 2. Okay, this one does, right? The root also has descendants of type 2. This one doesn't, this one does, this one does, and this one does, and this one does, and this one doesn't. Okay, and this one does, and this one doesn't. This one does, doesn't, does, and does, and what else? And does. Okay? Okay, so basically what did I do? I used 2 bits, right? So the yellow bit means that the node has descendants of type 1. The purple bit means that the node has descendants of type 2, okay? So the nodes that we're interested in this case are the nodes that have both bits set to 1, right? Okay, so you can think of them as booleans, right?
Right.
Okay. What do we do in general? In general, we have, instead of only 2 bits, we have this big K bits, right? Or booleans, right? So you have this big K bits. So start with, okay, which are booleans? Which are booleans? Okay. That indicate if a node has a descendant leaf of a given type. So, sorry. Type. All right. So how would we go about finding the nodes, right, that correspond, for example, for this little K2, right? So So how am I going to find the nodes that correspond to this send? What would those nodes look like in my suffix tree? Right? So I can actually draw that. Right? So let's suppose, so my suffix tree is going to look something like this. Right here I have send, right? Okay, it can have more nodes, but that's fine. Right? So I have send. Right? So what happens? I have a suffix here for the S1. Okay, so aller. Okay, $1. And I have something here, which is lot, $2. Okay, what does this mean, right? So it means that if I look at the bits of this node, I'm going to find that the first bit is set to 1, so the bit of string 1. The second bit is set to 1, so the bit of string 2. And all the other bits are set to 0, right? Okay. But I'm still interested in this. I'm still interested in this node, right? Why am I interested in this node?
The number of ones is 2.
Right. Okay. So to find out this number over here, I go through all of the nodes such that the sum of the bits set to 1 in those nodes is 2. Right? So I go through all of the nodes in the suffix tree, and for all of the nodes such that the sum is 2, I find the maximum string depth. Right? And to find this number, I go through all of the nodes of the suffix tree, and I check if the sum of the nodes of the bits is 3, and then I maximize over the string depth. Okay, is this okay? Was this clear?
Yes.
Right. Okay, but be mindful of one thing. Yeah, that's okay. Yes, be mindful of one thing. I cannot repeat my search over all the nodes. It's okay, I can actually do that, right? So, okay, so we actually have several steps here, right? So, okay, but we'll see that in the next class, okay? So, but there are 3 steps that we need for this algorithm. We need to build the tree, we need to build the Boolean tables, we need to sum the number of bits, and then we need to scan the tree for the nodes that we want to find. Okay, but let's do that in the next class. That's fine. We'll continue from here. Okay.
Professor.
Yeah.
Should we put the Boolean tables inside the node struct?
Yes. Right. So you're going to need them, right?
Okay.
Actually, sorry. Actually, no, and that's the reason they are not there. You need them, but you don't need the space, right? So the time does need this, but the space, okay, so for your project, the space is going to be O of n1 dot n2 dot nk, right? What does this mean? It means that I can, I need the tables to compute these values, okay? So the CV values that are described in the in Gus field is the sum of the bits, right? So you only need to store these values, right? So you can compute these tables in such a way that you don't actually need the space, right? So you only need these CV values, okay?
Okay, thank you.
Right. So don't put it in the structure because you won't have enough space, right? So the space cannot go over this. Okay. All right. Okay, more questions? All right, so okay, so let's do the lab class for today. Are we okay for the lab?